Well, hello there, BC Calculus students. I hope that your AP tests all went well. If you have any questions about it, you can talk to me. I know I did get to see Allison today on Zoom and talk with her, and I talked with Melissa via Messenger right after the test. So I do have some indication on how things went. What we are going to do is we have one more thing to learn before we take our final, and this is something that is very often covered in the first year of college calculus. By taking the BC, you should be able to, with depending upon your college or doing your concurrent credit or whatever, you should be able to get credit for the first year of college calculus. And so this is something that oftentimes is covered but isn't on the AP test, so we need to make sure we go over it. It's a technique of integration called trig substitution. Now, I'm going to go through this probably quicker than what you can write down. I'll fully explain everything, but just be ready to pause the video as needed in order to write things down. So, there's three main situations that we use trig substitution for. One is when we have a situation where we have something where we have the square root of some a squared. Notice a here is a constant minus u squared. U is some function. Oftentimes it's just a straight variable of x, but it could be a function. It could be something like you could have a 2x in there that's squared, or you could have something different, other type of function in there. But just be aware that that's in that situation. When this is the case, you're going to let u be equal to a sine of theta. And what that does is that creates a right triangle of the following situation. So the key is here, and the truth is you're always going to want to draw this triangle. It just helps you throughout the whole problem, you'll see. But what you're doing here, and I'll go over this one in detail, for 2 and 3 I won't go over in such detail. But what you do here is you want to get this as one of the sides of your triangle. And you recognize, based on Pythagorean theorem, that if you have these two sides, a and u, notice this one is minus this one, so this a has to be the hypotenuse, because that's where you'd subtract this. So if you call the hypotenuse a, you generally will always call the variable the opposite side the u. It would actually work if you called this u and that, but it's better if you let this be the u. And then this side here becomes the square root of a squared minus u squared, which means that we can look then, what we can say that this side here is equal to, notice if I look at this here, what I see is that if I look at this here, I could say what involves this side and the a here is I know that the cosine of theta would be this over a. So if I simply solve for this by multiplying both sides from a, I get that square root of a squared minus u squared is just a times the cosine of theta. And from that, I usually have enough where I can do my integration. All right, so we'll move through these others pretty quickly. When we have a situation where we have the square root of a squared plus u squared, now notice this is a situation where you want this side to be the hypotenuse, and you use the tangent ratio. So notice this side becomes the hypotenuse, the opposite becomes u, the adjacent becomes a. So we let u be that. And then that makes our hypotenuse a times the secant of theta. Okay. So next what we see is when we have u squared, so now we have our variable part or our function part minus our constant part. Now in this case, we're going to let the u be secant of theta, and this is still going to be the hypotenuse. Sorry, the u will be the hypotenuse there. And we will have the constant be the adjacent side, and then we get this being equal to positive or negative a tangent of theta. All right, so let's go ahead. Let's look at how we solve some of these. So I'm going to work 2 examples. I should say examples. One easy one and one a little more challenging. So here's our first one. We want to integrate the following. So one thing to look at, sometimes you can do these problems just with straight old u substitution. If you can, go ahead and use u substitution. But if you can't, you need to use trig substitution. And in this case, we do have to use trig substitution. So as I look at this here, notice I see in my square root, I've got a constant minus the x squared. That's like my first type of situation. So what I'm going to do here is I am going to sketch my triangle. Always start with sketching the triangle, because even if you know what to let x be equal to, it's going to be confusing at some point because you got to substitute in. Always start by sketching your triangle. So I know that this 9 here has to be the hypotenuse squared, since that's the only way you'd subtract it on the other side. So that's going to be 3. This x squared, remember, make it the opposite side. That's x. And that makes the adjacent then the square root of 9 minus x squared. Now I can figure out, so now remember, I want to find out what this is equal to. So in this case here, if I look at theta here, and I involve these two here, I know that the cosine of theta is this over 3. So multiplying 3 both sides, I get that this is equal to, so there's my cosine of theta is equal to this over 3. Multiply both sides by 3, and I get that the square root of 9 minus x squared is 3 cosine of theta. Now I need to account for x. So for x here, what I'm going to do there is I'm going to involve just the constant side in x. So I know the sine of theta is x over 3. Multiply both sides by 3, and I get x is equal to 3 sine of theta. Now the only other thing I have to account for is I have a dx in here. So what I'm trying to do is substitute totally for x and have it all in terms of theta, and then get something that I can integrate in terms of theta and then substitute back to x at the end. So what I'm going to do here is I need to substitute for dx in terms of theta. So if I take the derivative of x, if x is this, then the derivative of x, the dx, would equal the derivative of sine, so 3 cosine theta d theta. Remember, dx d theta multiplied by the d theta using differentials like that. Should be something you're familiar with, very similar to when we did u substitution. Now I can substitute in. So instead of dx, I will have 3 cosine theta d theta. Instead of x squared, I will square this, so I will get 9 sine squared times, and in my denominator, I will substitute here for this, the 3 cosine of theta, and I have the following expression. Notice the good news here, 3 cosine theta over 3 cosine theta cancel out. So I've just got d theta over 9 sine squared theta. But using simple reciprocal identities, I know 1 over the sine is the cosecant. So this is just 1/9 times the integral of cosecant squared theta d theta. And this is one of our known derivatives. We know that the derivative of the tangent is secant squared. The derivative of the cotangent is negative cosecant squared. So antiderivative is just going to be negative cotangent of theta, which I can write as negative 1/9 cotangent of theta plus c. Now my final step is I have to go ahead and I have to get my answer in terms of x. So here's why you always want to draw your triangle. You go back up here and you say, oh, cotangent of theta. Here's theta. Tangent's x over this. Cotangent would be adjacent over opposite. So my final answer is going to be negative 1/9 times square root of 9 minus x squared over x plus c, or more commonly written, just put that 9 in the denominator. And if you wanted to, you could take the derivative of this and you would find out that you would get back to that. That's a nice thing, is you can always take the derivative. Sometimes it's easy to take the derivative. Sometimes it's not so easy to take the derivative, but at least you have that option in order to check. And obviously for checking too, you have the advantage of using, if you have your CAS calculator, you can check it with your CAS calculator. I would suggest, but of course I expect to see all the work, so you better know how to do it. All right, let's look at another example. Unfortunately, I don't think I originally thought I was going to do 2 examples, but I definitely needed to. So this is going to be a little crowded, but I think we'll make out okay. So now we are going to integrate the dx over x squared plus 1 squared. Now, initially here we may say, wait a second, this doesn't have any square root. This doesn't look like a trig substitution situation. But I can write this with a square root here. So I can write this as dx over the square root of x squared plus 1 raised to the 4th power. So now I see that I do have this where I've got plus under my radical. So I'm going to set this up using my right triangle. And this, since it's x squared plus 1, this will have to be the hypotenuse. So I make this the hypotenuse. The opposite side will be the square root of x squared, which is x. And the adjacent will be the square root of the 1, which is just 1. Now from this, I can go ahead and I can start to set up. So I know that solving for this here, I know that if I look here at theta, I know that the cosine of theta would be 1 over this, or I could say the secant of theta is this over 1. So I just know that's the secant of theta. And I know that theta would be equal to x over 1. Sorry, I say the tangent of theta is x over 1. So for x, I could just say that's equal to the tangent of theta, which makes our dx secant squared of theta, d theta. Now I can go ahead and I can substitute in. So going back here, substituting in for dx, I have secant squared theta d theta. And then substituting in here for this, I have secant to the 4th. Well, notice this 2 of these cancels with 2 of those, so I get the integral of 1 over secant squared theta d theta. Using reciprocal identities, that's going to be equal to the integral of cosine squared theta d theta. Now it is possible that you have this one memorized. I don't. I need to use power reducing identity, as you do too, unless you have it memorized. Most people don't memorize this one. So we have to reduce this power here. So if you have a question about this, join me on Friday in Zoom and I can show you again where this comes from. But the power reducing identity there, I know cosine squared would be 1 plus cosine of 2 theta all over 2. So now I don't have the power anymore. And now I can integrate this. Notice I would distribute this 2 into each of these. So basically I would have 1/2 plus 1/2 cosine 2 theta. So when I integrate, the integral of 1/2 becomes 1/2 theta. The integral of 1/2 cosine of 2 theta, that's a quick u substitution, so you get the extra factor of 1/2. It becomes 1/4 sine of 2 theta. If you want to quickly check that, take the derivative, you'll see you will get to 1/2 cosine of 2 theta, plus a constant. Well, I've now got the integration done. Very nice. The only problem is my answer is in terms of theta. I need it in terms of x. So let's go back and let's look at how we're going to change this. So first off, I've got to replace theta with x. Well, look at here. X is tangent of theta. So in order to replace that, I would just have to look here. Well, first thing I've got, before I work with that, let's go back to this here. We don't have 2 theta anywhere here. So I have to use my double angle identity to simplify the sine of 2 theta back to, we know that the sine of 2 theta is 2 sine theta cosine theta. So the 2 cancels with the 1/4 to give me 1/2. And then instead of sine of 2 theta, you've got sine theta cosine theta plus constant. Now as I go to substitute in here, what I'm going to find out is I factored out the 1/2. Since x is the tangent of theta, theta is the inverse tangent of x. And so we have the inverse tangent of x there. And then when I go ahead and I know the sine of theta, notice the sine of theta, go back, look at the triangle. It's pretty easy to see the sine of theta is just going to be x over this times the cosine, which is just 1 over this. So you multiply those 2 denominators together, you just get Square root times square root, so it's just x squared plus 1 in the denominator, and the numerator is just x. Okay, that's trig substitution. So on your exercises there on the packet that that is included as a part of the assignment, you need to do exercises 6 through 16, all of those. And so that should be attached to the assignment when you go ahead and click on the assignment. Okay, hope it goes well, and we'll see you with another video tomorrow.